Hey folks, how's it going? So today's we're going to be looking into designing Google Drive by LXU. So we can think of Google Drive as a file storage, right? So we're storing this data on cloud, right? So by storing this data on cloud, so this service is going to allow us to then have synchronization, so we can actually access those files that we stored on cloud using different devices, right? So that's all it is to this. So one example might be Google Drive. Another example might be what is it? I think it's also there's Apple. What do they call it? iCloud, right? So I think there's also iCloud. Then there's OneDrive. I think it's from Microsoft. So yeah, these are the kind of services that I'm talking about, and we have to design similar system, right? Um, so this system is quite intense, like for us to design it here. So we need to pretty much come up with a set of functional requirement to reduce the scope of this system. So, what are the things that we should take into consideration, right? So, the first thing that we should take into consideration is that we should be able to enable the user to upload their file. So, we have to build um, these systems, services. So they are not necessary services. Before I continue, I just wanna say this. I've seen someone on LinkedIn saying that creating services for every like function, it's just an overkill, and I do agree with them to some extent. Like you can't have a service like upload, download service, all of that. So I'm just like creating services for the easy of explanation, right? But in real world scenario, I do believe that yes, like um, sometimes like creating like multiple services for each function might be an overkill because of microservices are quite difficult to handle. So just bear with me here. Uh, then we said that okay, we're gonna enable the user to be able to download, and we have to then be able to sync the file. By sync the file is that if the user uploaded this file on their mobile app, right? So if they uploaded this on mobile app, we should be able to allow them to see it um, right on the web. So the synchronization between different devices should be quite fast, and we should be able to notify the user, send some sort of like a notification system. Um, those are the functional requirement. We can think about others as we progress along, but I think these are okay for now. Uh, what is it? Then we're gonna think about non functional requirement. So these are the most important functional requirement as well, because of they're gonna like help us to know how which of the how we design the system, right? Like how do we select these each component to support the system. So for instance, like if you're gonna say that okay, I need a reliable system, right. um so by a reliable system is it means that I cannot afford to lose the data. Data loss is just unacceptable, right? We can't accept to lose the. You can imagine that someone uploaded their image. We can't accept to lose that. So we have to come up with like different um, strategies to achieve that, right? So, and we gonna say that bandwidth. What is it? Bandwidth usage. So you can think of this as nothing but we are saying to ourselves that we don't want to take a lot of like network bandwidth, right? So how you can think about this is that like let's say the user is using like their mobile data, so this like it's gonna get depleted quickly, right? Because of like the network bandwidth is way too high. So we have to come up with strategies to make sure that this is not the case. So right, um, what else? Scalability is always important factor. So we should be able to handle large load, like large traffic. Then high availability is also an important component. High availability. So yeah, meaning that the system should be always like available, right? So even if one server like dies, the system should be always available. uh I think then we're gonna look into fast sync speed. So the idea here is that we want to make sure that the system doesn't take too much time to sync the files that the user uploaded on their mobile device to maybe like web if they access them on their computer or something like that. So we want to make sure that the synchronization it's actually very fast, right? So now that we have our functional requirements and non-functional requirement in place, so now we're gonna have to then estimate the capacity load of the service. um, so essentially, this is one of the also important step in system design because it enable us to understand the expected load, and this will then influence how we design the system, right? So we do understand that okay, we're gonna be having this query per second, so we have to have a scalable system. So we can justify why we need to design certain things because of this capacity load. So that's why I'm just trying to make sure that you understand the importance of this. So all the time we're always going to make assumptions when it comes to capacity load. So we, for instance, for now we can just assume that okay, there's going to be 15 million of users that have already signed up, right? um, and among those 50 million of users, maybe we can assume that 10 million of these users are going to be active on a daily basis. So this is going to be our DAU, daily active users is going to be 10 million, right? So it's quite normal for us to make these type of assumptions. Um, or you, if you don't want to make these assumptions, you can use like existing services like Google Cloud, and you can actually get their number of users, but it's going to be roughly in the same amount of users like if you like iCloud or anything like that. So it's still okay. So based on this, we can also make sure that we assume that every cloud service gives you something like 10 gig, right? I know with Microsoft Drive, I think it's 2 gig. Then with Google, like Google Drive, I think it's 15 gig. I'm not sure, but we can assume that okay, every user get this free um, storage, right? So based on that, we know that okay, uh, the total the total space that we should be allocating, total space allocation is going to be 50 million by 10 GB, so which is going to be 500 petabytes. So there's quite a lot of data that have to be stored. Um, then we can look into the query per second, which is also another important metrics for establishing the load of the system. So we also gonna make few assumptions before we calculate this. So we can assume that um, what is it? There's gonna be two uploads, right? There's gonna be two uploads for each user every day. Two uploads for each user, like each active user from this 10 million DAU, because those are the active ones. So we're gonna expect 2 million users to upload, I meant to say. So which means that from our 10 million users, then we're gonna multiply this by two because we're saying that each user that is active on a daily basis makes two upload. Then we're gonna convert this to we're gonna divide this then to seconds so that we can get query per second. So this is going to be 24 because this is currently paid a day, so we need to go to seconds. So we're gonna say 24 divided by 3, uh, 3.6 seconds. So this is gonna give us 240. So what this number means is that we are querying the system every second, right? Um, this we're making 240 queries every second. That's what this thing means. Okay. Yeah, because of the making two uploads. Anyway, it's a query, right? You making a request when you upload, so it's still fine. Anyway, we're gonna say that the read and write ratio is gonna be 1 to 1. Um, Read ratio. So being able to understand the ratio, the read and write ratio of the system is quite important because it can establish how you're gonna be able to select your databases. There are certain databases which are much more good if you're gonna do like writes, and some databases are good if you're gonna do like a lot of reads. We're gonna get into like those as we continue with our system design journey. Um, so so this is just a number that we expect, but then the distribution of the queries might not be even. So to save us from just assuming that the query per second is 240 at max, we can actually multiply this by 2. Then this is going to give us the peak that we can expect. So it's going to be, the peak is going to be 480. Okay. Um, I think that's like the core. Actually, the most important thing that we can talk about is the bandwidth. So let's calculate the bandwidth because of the bandwidth. The reason I want to calculate the bandwidth is because it's among the what is it? It's among the most important um, non-functional requirements. So I think it's important for us to calculate the bandwidth as well. So how do we calculate the bandwidth of the system? Just to know the load as well. So we have few assumptions that we made, or few assumptions that we should make. Is that okay? Let's assume that we said that users upload 2 files, right? We agree on that, right? Each day. But what's the size of those files? So let's assume that one file is going to be 500 KB, right? Then maybe because of these 2 files, then this is going to give us 1000 KB, right? So that's fine. Then we can, because of this is per day, so I can actually convert this to, I can convert this to gig. So I'm going to work with gig because of I think most of the system calculate their bandwidth and using gig. So I'm going to use that. So I'm going to convert this KB to gig. So we're going to say 1000 KB divided by 1024. It's going to give us approximately around 0.97 GB per day, right? So that's what we're going to have. So uh, that's the bandwidth for one file. So this is one file. So we know that we said that we have 10 million users. So we need to multiply this by 10 million users, right? Because of, we know that our day use 10 million. So this is going to give us 9.7, I think 9.765, whatever, but in something like millions, then it's going to be gig per day. Yeah, if you don't want to write gig, I think it's going to be 10 terabyte. It's just simple and short. So you can just say 10 terabyte. Um, then we need to now get to seconds because we said that this is a day. Because of like with bandwidth, the trick is that you wanna say gig per second. You want your metric to look something like this. So currently our metric is per day, so we need to convert this number to a second. So which means that we're gonna take this 9.7 something gig, then we're going to be dividing this by 24, by 3.6 to convert this to seconds. Then this is gonna give us, it's gonna be 10 terabytes, so it's gonna give us 113 or 120. Yeah, you can actually, it's fine to round it off, round it above. Actually, it makes sense. So you can say 120. Yeah, 120 GB per second. So yeah, it's gonna be 120. So because of we said that the reads and write, it's one to one. The reason we said one to one, by the way, is because I don't know if some of you are aware, but when you use your Google Drive or your iCloud storage, um, like you hardly read the files, right? And every time probably when you upload you view the file, so that's like, I think it's an appropriate assumption. Unlike, like, you can think of like YouTube, like the reads are high, are way too high, right? Like people view YouTube than they actually upload. So that's fine. Anyway, so which means that this is going to be our bandwidth. So 120 gig per second, the system has to take that. Every second we have to handle 120 gig. So that's what this metric means. Because if we said that it's one to one, so that means for upload as well as download. Okay. Um, yeah, this is like the same metric. So now let's propose a high level design of our system. So this is not necessarily an optimized system, but it's just to let us think about the important components that we should be optimizing. So at heart of this system, we can think that we have a server. This is going to be an important component. So the server essentially, it's gonna enable us to upload as well as download. So we have to hit the server. Okay. So two, we gonna have to have a database. So this database, it's gonna be storing the user information, right? So so it keep track essentially of all the metadata. Three, we're gonna have to have, because of we storing the files, so we need to have some sort of like a storage system. So you can think of this as nothing but something similar to S3. So it's gonna store like the data for us, right? um so when it comes to this, so this is more like a file system. So you can think of like you have a directory like drive, right? And then under this, you can have like namespaces, um, and under these namespaces, you can have the files of the users, right? Like let's say file.text, file.png, something like that. So that's how like these files storage are structured. It's just a file. So we can now talk about, so like I said, this is just purely like we thinking up high level about these components separately. We're not optimizing anything as of yet. So we can think about APIs. So one thing that we know is that we're gonna have to upload our files, right? So we need to hit some sort of like an endpoint that is going to enable us to upload these files. But this upload API, it's gonna have a parameter called upload type. So because of users can upload like very huge files, what will happen is that some of the files can be interrupted due to the network. So we want to enable them to resume the upload. if something like interrupted their system. Imagine like you're uploading something like 4 gig file, right? And maybe along the line, like maybe around like 2.5 gig, while you're still uploading, network hit you in South Africa. We maybe it's like load shedding, right? So what will happen then is that like you can resume from that 2.5. We don't You're not supposed to start like from zero and all the way, right? So that's what this upload type is going to do. So another parameter it's going to take is the data. So you have to point it where the data is. So this is going to be a local file on the user's system. um, So yeah, so that's that. Another API endpoint that we can think about is probably gonna be download. So download is just gonna be it's gonna be easy because it's a get, right? Request. So yeah, so it's gonna be download API, download APIs, and the params here will be you pass it the path of the weather files that you want these. So I can think here, maybe this is Hector. If I'm logged in, probably the namespace, I don't need this. Um, Maybe this is the folder that I created and whatever, dot, maybe text, something like that. But that's going to be the download API. We can look also into get file revision. So this is nothing but you can make a get request as well to get the file revisions. So let's say you have a file. So let's say you have a file like path. This is like your params. You have like this file here, Hector, the same file, right? .txt. Then maybe we can limit the vision. We can have some sort of like a pagination, but the punchline is that when you make this request to get revision, you're gonna get like also like the previous versions, um, right? So maybe the user has made changes and maybe they wanna revert back. Yeah, that's what this means. Anyway, these API that we have here, we're gonna make sure that we require user authentication, require user authentication. So most of the time, like APIs, like we have some sort of like a token, depending on like if we're using JWTs, but we're gonna require authentication from the user, as well as we're gonna make sure that this is we're using the HTTPS. So this is the secured socket layer that protect the data on transfer, right, between the client and the backend system. So the data is protected, so that's why we're gonna need that. Did mention that we're gonna actually be requiring the server, the database, as well as the storage system. So we mentioned all of this as if like our system is going to be a single server setup. So we need to decouple these systems. And secondly, if we're really going to be building like a file system like from scratch in house, then there's going to be a lot of challenges because currently we said that we need a storage system, but then you can imagine that there's going to be a lot of users uploading like data, right? So this storage that we have is going to run out, right? Maybe one can say, but okay, we will shut the data then, right? We will distribute the data across multiple file storage, right? But then this raises another question. What about like data loss, right? How do we maintain data loss, right? And how do we do things like geo replication? Do we have like, can we able to access data centers across the globe, right? So to avoid us going through this headache, we can actually use S3, right? Like we can use S3 storage. like because of it's cheap, and I don't think that there is too much. We should be thinking about like trying to build it ourselves, unless if like you're working in a very sensitive like company whereby like they don't want like data to be on Amazon or like other cloud providers, then yeah, you can actually think about going that direction. But in this case, like I think it makes sense for us to do that, right? So the thing about S3 is that it enables you to support same region to get like the cross region replication. So it's scalable, right? So that's the advantage of this. And another thing is that it safeguards you against this data loss, because of you can store data in like you can replicate data across like multiple regions. So this also ensures like data availability. So even if one shard goes down, or one replica go down, like the user can read from another replica. So it saves us a lot of pain. So that's what we're gonna need, right? So to decouple our system, we're gonna make sure that our API server, which is gonna be horizontally distributed, we're gonna have a load balancer, right? We're gonna have a load balancer, and we're gonna have the S3 bucket that we spoke about, which is gonna reduce a lot of heavy work for us. There's no need for us to really implement that. So the load balancer is gonna help us to evenly distribute the load, the traffic load, to these servers that are gonna be enabling the upload as well as the download. Then we spoke about as well as the metadata, right? So we're gonna have the metadata as well, and we're gonna decouple it from the server. So this is to avoid a single pointer of failure, because if they're stored here, like if the server goes down, then the database for storing the metadata is also gonna go down. So it's good idea for us to decouple these things, and we're gonna talk about how we're gonna shard, right? We're gonna shard this data to meet the availability as the requirement as well as the scalability requirement that we spoke about. So we're gonna need to talk about data replication as well as sharding mechanism or techniques that we can use. So now let's try to think of how we can actually be able to sync conflicts, right? So by syncing, I mean like imagine if you have enabled your friend to make edits to the file that you have on cloud, and you're also making the changes as well, then there's going to be conflict. So let me try to visualize this. So let's assume that this is you and you making edits to this file. This can be a doc file, it's fine, and you have given your friend the right to also make changes. But imagine if you, right, you make changes to this file. Like let's say you get the file, it's on your local, then you make the updates, right? Then while the file was on your local, your friend got the file and was also trying to make the update. But you made the changes to this file, like your latest changes to this file, right? So now your friend also tries to say, okay, let me now update. Then they're gonna get a conflict, right? So essentially, in simple terms, this conflict happens when the user tries to modify the same file or folder at the same time. So the conflict is gonna occur, right? So how can we solve this? We can solve this by saying that what will happen is that if the user makes the updates, right? While this user is still like busy with like the previous version and this user updates this user is gonna get a conflict. Like we're gonna show them this red thing. Then we're gonna show them that okay, this is the latest changes, right? And this is your current file. So they will be able to see two copies, and they will be able to see that this user has made these changes here or somewhere here, right? So that's how we can work through this synchronization problem. So now let's try to consolidate all the components for our high level design. So I'm going to start here from the user so that I get to show you the flow of how the uploading and downloading of the file will look like from our system. So we did talk about that we're going to need the load balancer. This is because if we wanted to evenly distribute the load of the system to our servers. So these API servers, they're not necessarily going to be uploading the files, right? So they are mainly responsible for things such as user authentication. They are mainly like managing user profile, updating the metadata, all of that. So that's what these API servers will be. Another important thing that we're going to talk about is that we're going to need to then have these what we call the block servers. So this is going to be important for uploading these files to the servers. So we call them block servers because how they work is that they split the file into several blocks, right? Each with a unique hash value, and these hash values are going to be stored in the metadata. But these blocks are going to be stored in the cloud storage. So this is could be our cloud storage like S3, like we spoke. So it's going to be S3, right? So to construct the file, because we're saying that we're storing these files as blocks, to construct the file, then we need to join these blocks in a particular order. Then we're going to also have the cloud, the cold storage. So this is going to be the files that we do not actually access much more frequently. So this is going to be the cold storage, right? Um, then we're going to need to have our metadata, right? So the metadata, it's going to store like things such as the visions of the files, right? So it's going to be stored in our DB. We're going to have a cache of this metadata to speed up the reading of this data. We're gonna also have the notification service. We're gonna need the notification service. So this is gonna be the publisher subscriber system that is gonna actually enable the user, right, to get any notification if like we made changes on the files or people are making changes to the files that they are currently editing. They can get notified that okay, you know what, someone removed, someone edited, or someone did that. So then we're gonna use the long pooling so that we can detect these changes here. Okay. Um, we're gonna be having also the offline offline backup queue, right? So what happened is that the client can be offline, right? So they cannot pull the latest changes. So the changes that they're going to be making on their local device will then be queued offline, right? Because of they are not online. Then what will happen is that when they get online, when they become online, then we can actually be able to sync all the changes that they made, um, right? When when they're online. So that's why we're gonna need this message queue right here, which is gonna be offline. So now let's go into our deep dive of the system design. And the first thing that you must be curious about is this block server, right? It's this thing here that we just introduced. So remember that our requirements when we started with our system design was that we said that okay, we want to reduce the bandwidth, right? We want to reduce the bandwidth. So how does this the block enable us to achieve that, right? So how it works is that how we can think about it is that you have a file that is going to be split into different blocks. So let's say this is your file, then we split this block into like block one, we split this into like block two, all the way to block n, right? Then Now that we have these blocks, what we're gonna do is that we're gonna compress this block here. So we're gonna use like compressing algorithm. This could be gzip or something like that, but we're gonna compress these blocks, and then we're gonna encrypt, um, because of this was also part of the requirement. We're gonna encrypt these blocks, then we store them as we said in this cloud storage, which we said that it was gonna be S3, right? But your reason might be, what's the purpose? Why are we doing it this way, right? So you can think that the first thing that this thing allows us to do, which right, is that because of now we are storing these files, right, and we have compressed them, so the bandwidth of storing them in this cloud storage, it's way, way, way too small, right? So we're reducing that bandwidth because of we compressing these files, we're making them to be small when we store them inside there, and we chunk them so it becomes much easier. But the chunk, like the reason we create blocks, the main advantage comes when you think about how we have to do the updates. This is where you're gonna appreciate the block. Imagine if like you have a file, this file probably was like 4 gig, all right, and we store it in the storage. But now you made like changes, like small changes to that 4 gig file, right? So you made four small changes. So instead of us really trying to then do the same process whereby we have to now chunk the file like create blocks and compress and encrypt, nope, we don't do that. We're just going to check um, which block have been modified, right? So you can think like say block 10 has been modified. That's the one that is going to be stored in cloud. So the other blocks are going to be unchanged. So the advantage is that like you can think of like each block is probably like 4 megabyte. This is the only thing that we're gonna change, right? Because of the whole entire file is on cloud, right? Like because of like the other blocks haven't changed that much. So that's the advantage of us actually using blocks. So just to iterate, they enable us to make sure that we upload these files much faster in the cloud storage. They reduce the bandwidth because of these blocks are compressed. Secondly, the updates of these files are much more efficient because of we do not have to like get like upload the 4 gig again every time we make like small changes, but rather like we just like update the block that we changed. So now, how can we achieve high consistency? By consistency, I'm referring to the fact that we want all the users to see the changes like that have been made at the same time, right? So we don't want like the users to get like stale changes, right? Like the user get the changes, but the other users does not get the changes, mainly because of probably we used a different replication strategy, which probably adopted the eventual consistency model by default. So we have to then think about ways we can actually avoid that, right? So how can we do that? The first thing that we can do is that we can invalidate the cache database. So that's the first thing. So let's go to a high level design, because remember that we said that the metadata will be cached here. But you can imagine that if we make the updates, right, like for specific file, right, then that file probably like was cached previously. So we haven't made the update within this cache as well, because of we have to like go to that cache and say, hey, this file here, this change here is no longer valid, like because of the file has been updated, something along those lines, right? So that's where like invalidate cache um, is quite important. So what will happen, how we can think about it is that every time we make the updates to the database, what we want to do is that we want to then mark that file in the cache to be invalid, right? This is because of the file has changed, so we don't want the user to read that file. So they would rather go directly to the database to actually get the the update, the recent update, right? Um, So we can also say the data in cache and replicas must be consistent. The data in cache replicas and masters must be consistent as well. Okay, so for us to achieve this, we're gonna have to adopt the relational databases, right? Because the relational database, they provide us with what we call ACID, right? So this is like atomicity, consistency, isolation, and durability properties. So that's what they provide us. So we can't get these things if we're using something like NoSQL database. So yeah, so we can be able to achieve consistency if we use the relational database. So that's how we're gonna be able to store all these files visions within this metadata base, right? So, but the punchline here that you can take away is that we can be able to show the users, all the users, um, consistent changes, updates, right? Because we're not relying on the eventual consistency model, which is might have caused problems. So we're relying on the strong consistency because we're using this relational database, which has the ACID properties, as well as we're making sure that all the cache data within our cache is invalidated, just to make sure that the data that is within the cache is like the user is not reading like outdated data, something like that. So we have these two things in place to make sure that we get consistency. One of the most important components from our high-level design was the metadata database. And we said that this is going to be a relational database, but how are we going to then represent the schema? So we need to think about all the fields that are going to be quite important in the tables, right? So the first table uh, is going to be the user, right? So it's going to have the user ID, and we're gonna have the workspace, right? So this is gonna be the root directory of the user. So it's gonna be the workspace. So the workspace is gonna enable us to know um, the owner ID, which is gonna be the user ID, as well as the ID of the workspace. And this can be shared. So we can say it's shared or something like that, and we can have created at, right? And the workspace can also be linked to this file, right? So a file table store everything related to the latest file, right? So you can think here we can have a file. I'm gonna omit certain fields, but you have a file name, you have an ID of this file, you have like relative path, right? You still remember when I told you when we started that these files are stored on S3, not on the unlike a relational database. Here we store like the relative path where this file is, so that when you want to get the file, you can just hit the you can get the file path. So that's that. Then also we're gonna know which workspace this file is within. So this is gonna be an ID. Okay. We're also gonna have file visioning table. So this table is going to be responsible for keeping the vision of the file. So you can think here we're going to have a vision number. So which means that this table is going to be it's going to link to this. Here you have an ID, you have a device ID as well as file ID, something like that. Okay. Um, then you're going to have also the device table. Okay. So the device table is gonna show the user ID, the device ID, all of that information is gonna be inside here. We're gonna also need to keep the table for the block. I don't know if you still remember, but one thing that we said was that we wanted to store everything related to the blocks, right? I don't know, maybe I might have forgotten to mention that. but we have to store all the metadata related to these blocks within the metadata table. So that's why we also need some sort of like a table to store this information. So we're also gonna need the block here. So we're gonna have block ID, something like that. This is gonna be the user ID. It's gonna be important, especially when we want to construct the file, something like that. But this is a high level schema. We might have missed a lot of tables, but it pretty much gives you a high level idea of like the important pieces that are needed for us to store this data. Okay. Okay. Given that this is our table, right? This is our schema meant to say, and this is our high level architecture that we spoke about. How will then, when the user upload the file, how will the uploading process looks like, right? So we can think that the file, by file I mean it could be the text, it could be MP3 file, it could be literally anything, right? It's gonna go through this path, right, of the block server. Then for the metadata of that file, it's going to go through this path, right? The date of the file was uploaded, all of this stuff is going to go through this, the relative path, um, all that information is going to go through this path because of it has to be stored inside this metadata database. So now the question is, how will this process look given that now we have this table? So what happened is that the user is going to upload the file, then the metadata of the file will then go to the metadata table. Then inside this table, we're going to insert a new row. Then we're going to have a status to say pending here, right? So because of the file is not yet uploaded, remember that um, there's another process that is still like uploading that chunk. So we need to update the status when that process is done. So for now, when we upload the metadata, because this is going to be faster compared to uploading a file, so this is going to be much faster. So we're going to upload that. Um, right. So upload metadata to DB, right? So now the second process is the one that is going to then upload the content of the file to the block servers. So we know that the block servers are going to chunk the files into like multiple blocks. We spoke about this. Then it has to compress, encrypt, and upload them to cloud storage. But once the file is uploaded, the cloud storage is going to trigger upload completion callback, right? The request then is going to be sent to the API server. So what will happen is that this guy here, the cloud storage, is going to have a callback that is gonna trigger to call the API server to say that yes, we have uploaded this file successfully. So what will the API server do is that it will go then to the metadata and tell the metadata that you can change the status then from pending to uploaded. So this is going to be changed for this ID. Okay, so that's how the workflow of us uploading a file will look like. So how will then the download look like? Before we continue, I just want to say that I missed an important step, which is that essentially because of the status here on the metadata will be updated to updated, we need to notify all the users that okay, the update has been this file has been uploaded. If like these users are working in the same file in the same workspace, right? So we're gonna do this using this long pudding to update those users, right? Um, okay, that's that. But then the question becomes, how will then the upload looks like, right? So there's an edge case with like, not upload, sorry, I meant the download. So we looked into the upload process, but now we need to look into how the download will work. So the edge case with the download is that we don't want the user to download like old versions of the files. We always want them to download like recent version. Okay, they can choose. They can have an option to download like old versions, but um, or like old versions or something like that. So what we need to do is that we need to somehow get the file versions, right? Um, from the metadata. So we're gonna request the file versions, but before we do that, we also need to make sure that we let the user knows that the file is being updated currently, or the file has changed by somebody else. So this is because of, you can imagine that someone has made like recent update, but then the user was not aware of those updates. So the first thing is that get the latest update that have been made, or let the user know about if someone has changed something somewhere. Let them know. That's the first thing, right? So that they don't download like an old file or something like that, right? So um, once we have given them like the metadata, then the client can, using the metadata, the client can then choose which like version they want to download, or right, like they can pull all the updates and all of that, because the vision is always going to hold new updates, or they can get to decide on themselves. Then based on that, what they're going to do based on that vision, they're going to make a request now, not to the metadata but rather to the block server, because now they're going to get the file. So what will happen is that the block server first will download the blocks from the cloud storage, right? So remember that here we're storing those blocks. So it's gonna download all of those blocks, and based on those blocks, it's gonna then construct the file. Then it's gonna give the we're gonna send the file back to the user. Remember that we store the files. Like remember that what we said is that we store the blocks of the file, right? So um, so which means that there has to be some sort of like a relationship between this file vision and this block here, right? Because if we want to make sure that the file ID is gonna be having like multiple blocks that are constructed here. So hence it is easy when the user make a request, then we can construct these blocks, right? Because of the user has gotten the metadata. Like we do know which file version they want. I hope that makes sense. Probably that was not the best explanation, but hopefully I was able to give you some sort of like an idea. Um, yeah. So another important component that we should look into is this long pooling, the notification service, right? So we're using the long pooling because we want to persist the connection from the client to the user. So the reason is because of we want to be able to update all the users about like the changes that happens to the files instantly, so right. So there's we could have used WebSocket, right? But the problem with WebSocket, the reason we didn't use them is because they are bidirectional. So how you can think about it is that you persist the connection between the client and the server. So the communication is going to be bidirectional. But in our case, we don't need the client to send like we don't need to listen to the changes from the client, uh, right? The server sent information about the file changes. That's our use case. That's why in this case we're using long pooling. According to also LXU, he said that Dropbox uses long pool, right? So we can be sure that long pooling is gonna be scalable. So what I want to talk about now is really us to think about the failovers, right? So what could go wrong um, with the system at the current moment, right? So, so the first failover that we can think about is going to be the load balancer. So, like I said, that the load balancer, like at the current moment, if like we don't have the secondary LB, it's a single point of failure. Just to show you from the architecture to remind you that if this thing goes down, then how are we gonna distribute the request to different API servers? So we need to have a secondary load balancer. So what the secondary load balancer will do is to ensure that if this first load balancer fails, it's going to take over and handle all the incoming requests. Okay. The second thing that we can think about, the second failure is going to be the cloud storage. So the cloud storage, uh, you can think of like the failure here would have been that if one of the if one of the storage goes down, then we lost the file, right? Um, we lost all the data that is inside there. So we said that we can avoid this from happening if we then use this multi-region, right, whereby the data is being replicated across multiple regions. So I think you can also get the same thing with S3. So the punchline is that having these replicas, one, you avoid data loss because of if one replica goes down from one data center, you have another data that is being live from a different data set, from a different data center, right? And the second thing is that it helps because of now the users that are close to and their nearest data center, they can nearest data center, they can actually read from the closest replica. So that's another advantage with this. So it kind of like cover also the high availability, right? Yeah. Another failover that we should think about is that is our metadata database. So we said that we're using the relational database. So how we can share the data, we can use the master slave architecture, and then this will allow us to say that the master will take all the reads, all the rights will go to the master, and all the reads will go to the slaves. Then what will happen is that um, if the master dies, then a slave will be made, will be promoted to become a master, right? So, and then if a slave dies, then the the reads will be directed to the other slaves. So this is fine. So yeah, that's that. Then the metadata for we should also think about the metadata cache. What happens here? So the metadata cache, we can have multiple nodes, right? So if one node goes down, we can replicate the data within the nodes, and we can have these nodes replicated across multiple regions, so that if one node dies, then we still have another node. So we can also solve that problem that way. What else? The notification service failure. Yeah, let's talk about it. Five. So how can we handle the failure here? So let's say that each server handles like thousands and thousands of like connections, because we said that we're using the long pool connections. But now what happens when that server dies that is holding those connections, right? So how are we going to handle this? So we can actually restart a new server. So that means that all the connections that were connected to the server that just died will be lost, right? Then the user will have to reconnect to the new server, right, to establish the new connection from the new server. So that's how I think um, we can work around this. But the bottleneck here is that reconnection uh, with all the lost client is relatively a slow process, right? So this is like the one of the stuff that comes with long pulling, like the challenge, right? But yeah, I think that's what I had to say about this. Yeah, thank you guys very much for tuning in. I'll see you guys in the next one.